Today we shall study about combination of capacitors in electrostatics. There are two types of combinations. The first is series and second is parallel. As shown in the figure, the two capacitors C1 and C2. Two capacitors C1 and C2 are connected in series. So their charges are plus Q and minus Q. Capacitors C1 and C2. Therefore, the potential drop V across the combination is the sum of the potential drops V1 and V2 across C1 and C2. V बराबर V1 plus V2 बराबर Q by C1 plus Q by C2. इसलिए V by Q बराबर 1 by C1 plus 1 by C2. Now, for the potential difference V, the effective capacitance of the combination is C बराबर Q by V. इसलिए 1 by C बराबर 1 by C1 plus 1 by C2. For any number of capacitors, V बराबर V1 plus V2 plus that is Vn और Q by C1 plus Q by C2 plus that is Q by Cn. इसलिए 1 by C बराबर 1 by C1 plus 1 by C2 plus that 1 by C2 plus that 1 by Cn. Capacitors in parallel. In the parallel, we show the figure C1 and C2 are connected parallel, plus plus 1, plus are connected and negative are connected. So Q1 बराबर C1V and Q2 बराबर C2V. इसलिए Q बराबर Q1 plus P2, Q बराबर Q1 plus Q2. Now Q बराबर CV बराबर C1V plus C2V. इसलिए C बराबर C plus C2. Similarly, for n capacitors, C बराबर C1 plus C2 plus delta Cn. Now, energy stored in a capacitor. There are two capacitors C1 and C2. Charge Q dash minus Q dash. Minus Q dash minus delta Q dash increasing. Therefore, a capacitor is a system of two conductors with charge Q and minus Q. To determine energy stored in this configuration, consider initially two uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1 bit by bit, so that at the end conductor 1 gets charge Q. By charge conservation, conductor 2 has charge minus Q at the end. In transferring positive charge from conductor 2 to conductor 1, work will be done externally, since at any stage conductor 1 is at a higher potential than conductor 2. To calculate the work done, we first calculate the work done in a smaller step involving transfer of an infinitesimal amount of charge. Consider the intermediate situation when the conductors 1 and 2 have charges Q1 dash and minus Q dash. At this stage, the potential difference V dash between conductors 1 and 2 is Q dash by C, where C is the capacitance of the system. Next, imagine that a small charge delta Q dash is transferred from conductor 2 to 1. Work done in this step, delta W dash, resulting in charge Q dash on conductor 1 increasing to Q dash plus delta Q dash, given by delta W बराबर V dash delta Q dash बराबर Q dash by C delta Q dash. इसलिए W बराबर इंटीग्रल ऑफ डेल्टा W बराबर इंटीग्रल फ्रॉम 0 to Q, Q dash by C delta Q dash और 1 by 0 Q dash square by 2 from 0 to Q, इसलिए 1 by 2 Q square by C. Therefore, W बराबर Q square by 2C बराबर 2CV square बराबर 2QV. The electrostatic force is a conservative force, so the work is stored in the form of potential energy of the system. For the same reason, the final result for potential energy is independent of the manner in which the charge configuration of the capacitor 2 is built. Therefore, the energy is stored in the capacitor of 2Q square by C or A lambda square by 2 गुना D बटा epsilon naught. E बराबर sigma बटा epsilon naught. Energy is stored in the capacitor बराबर U बराबर 2 epsilon naught E square गुना AD energy density of the electric field U बराबर required 2 epsilon naught E square. Now, Van de Graaff generator. This is a machine that can build up high voltage of the order of the new million voltage The resulting large electric fields are used to accelerate charged particles, electrons, protons, ions, to high energy needed for experiments to prove the small scale structure of the matter. The principle underlying the machine is followed. Suppose we have a large spherical conducting cell of radius r on which we place a charge q. This charge spreads itself uniformly all over the sphere. The field outside the sphere is just that of a point charge at the center, while the field inside the sphere vanishes. So the potential outside is that of a point charge, and inside it is constant, namely the value at the radius r. We thus have potential inside conducting a spherical cell of radius r is carrying charge q by our constant 1/4 pi epsilon naught q by r. Let us suppose that in some way we introduce a small sphere of radius small r carrying some charge q into a large one and place it at the center. The potential due to the new charge has the following values at the radius indicated. Potential due to a small sphere of radius r carrying charge q barabar 1/4 pi epsilon naught q by r at the surface of the smaller sphere barabar 1/4 pi epsilon naught q by r capital R. Therefore, the potential V barabar at r capital R distance 1/4 pi epsilon naught q by capital R plus q by capital R. V at a small r barabar 1/4 pi epsilon naught q by r plus q by r. Therefore, VR minus VR barabar q बटा 4 pi epsilon naught 1/r minus 1/r capital. High voltage 3 गुना 10 to the power 3 गुना 10 to the power 3 volt per meter. The figure shown as the picture.